Hey, and welcome to The Explainer. We're going to talk about something pretty fundamental today. How do computers actually see relationships? I'm talking about everything from your social network to the fastest way to drive across town. It all boils down to one core idea.
So what do they all have in common? Well, the answer is pretty simple, right? They're all networks. At their heart, they're just these huge sprawling webs of connections. But here's the trick. For a computer to do anything useful with that web, like navigate it, it has to have a way to actually see it, to store it in its memory.
And in the world of computer science, we have a special name for these networks. We call them graphs. And honestly, it's a beautifully simple idea. All you've got are a bunch of points, we call them vertices or nodes, and then you have the lines that connect them, which we call edges. That's it, nodes and edges.
Okay, so to really wrap our heads around this, let's use this one simple graph as our guide for today. It's going to be our little lab rat. You can see it's got 5 nodes labeled A, B, C, D, and E, and there are 6 edges linking them all up. And this, right here, this brings us to the main challenge, the big question of the day. This picture makes perfect sense to you and me, right? But how in the world do you translate this visual idea, these dots and lines, into something a computer can actually read and work with? How do you turn a picture into data?
All right, let's get into it. Our first method for tackling this problem is probably the most straightforward one. It's called the adjacency matrix.
So think of it like this. You know those mileage charts you used to see on old road maps? The ones that told you the distance between any 2 cities? It's basically that. It's a big grid that just answers a simple yes or no question for every single possible pair of nodes. Hey, are you 2 directly connected?
And check this out. This shows the translation perfectly. Our little drawing of the graph on the left, it turns into this simple grid on the right. See? If you look at where row A and column B meet, there's a check mark. Boom, that's the edge between them. Now, what about row A and column C? It's empty. Why? Because there's no direct line connecting them. Simple as that.
So here's the nitty-gritty of how it works. If your graph has, say, n nodes, you just make a grid that's n rows by n columns. A check mark, or maybe a 1 in a real program, means, yep, there's a connection. You'll also notice it's a mirror image, right? The connection from A to B is the same as from B to A. But the real superpower of this method is its speed. If you want to know if 2 nodes are connected, you just look at one spot in the grid. It's instantaneous. We call that an O of 1 operation. Super fast.
Okay, but there's a catch. That matrix can get absolutely massive. Imagine a social network with 1 million users. That's a million by 1 million grid. So that brings us to our second method, the adjacency list, which takes a totally different approach.
Yeah, so instead of that giant grid that keeps track of every possible connection, even all the empty spots for people who aren't connected, this way is, well, it's more personal. Think of it like a contact list in your phone. For each person, you just have a list of their direct friends. You're not keeping track of everyone they don't know, right? Just the ones they do. And what's so cool here is how this represents our exact same graph, just differently. See that on the left? It's basically an array, like a simple list with one spot for each of our nodes, A, B, C, D, and E. And from each of those spots, you get another little list. Programmers call it a linked list that just chains together its direct neighbors. So you look at node A, and its list just has B and E. Look at B. Its list has A, C, and E. It's so much more compact. It's clean, it's direct.
The real genius of this structure is how efficient it is, especially when it comes to saving memory. Think about it. You're only storing the connections that actually exist. There's no wasted space. This makes it a total game changer for what we call sparse graphs. You know, the ones with tons of nodes but not that many edges connecting them.
Okay, so let's recap. We've got 2 totally different ways to draw the same map for our computer. On one hand, you have the all-knowing grid, the adjacency matrix. On the other, the super efficient contact list, the adjacency list. It's a real showdown. So, which one's better?
And the answer, which you're going to hear a lot in computer science, is, well, it depends. There's no silver bullet here, no single best way to do it. The right choice really, truly depends on the specific job you're trying to do and, most importantly, the kind of graph you're working with.
And to make that choice, you really need to get this key difference between a dense graph and a sparse graph. A dense graph is just, well, it's dense with connections, super interconnected. Think of a tight-knit group of friends on a social network where pretty much everyone knows everyone else. A sparse graph is the opposite. It has way fewer connections. A great example is a road map, right? Cities are nodes, but they're only connected by a few major highways, not 1 million little roads between every single pair. Okay, this table breaks down the trade-offs perfectly. Now don't get scared by the big O notation stuff. It's just a shorthand we use to talk about performance. So look at check edge for the matrix. It says O of 1. That just means it's instant. It doesn't matter if your graph has 5 nodes or 5 million, the time it takes is always the same. It's flat. For the list, though, you might have to scan through a node's friends to see if an edge exists. But now look at space. The matrix is O of V squared. That squared part is the killer. It means its memory usage just explodes as you add more vertices. The list, on the other hand, is way more chill, only using space for what it actually needs. And these are the exact kind of trade-offs engineers have to make every single day. So, what's the bottom line here? It's actually pretty simple. If you've got a dense graph and your main job is constantly asking, are these two nodes connected? Then the adjacency matrix is your hero. It's built for speed. But if you've got a huge, sparse graph, like, say, the entire internet, and you're worried about running out of memory, the adjacency list is, without a doubt, the way to go. And that's the core of great engineering, isn't it? Choosing the right tool for the job.
So there you have it. We figured out how to teach a computer to see a map of connections, how to store it in its memory. But you know what? That's really just the first step. Storing the map is one thing. Now that the computer can see the map, it opens up this whole new world of incredible questions. Like, how do we actually find the fastest route? How does a social network recommend a new friend? How do we find the most important person in that network? All of that requires algorithms to intelligently navigate these connections. But, well, that's a story for another explainer.